All right, so if you're in the Python world, you've probably heard the buzz. This thing called no GIL Python. The hype around it is huge, promising these massive speedups. But is it really the performance miracle we've all been waiting for? Well, let's dig in and find out. You know that feeling, right? You've written some multi-threaded Python code, you fire it up, and you look at your activity monitor and just one CPU core is pegged at 100%, while all the others are basically asleep. It's super frustrating. So what's going on there? Well, there's a very specific culprit behind this. So this one-core problem, it actually has a name, and it's something that's been part of Python forever. We're talking about the Global Interpreter Lock, or as everyone calls it, the GIL. Okay, so what is the GIL? Put simply, it's a lock. It's a rule baked into standard Python that says only one thread can execute Python code at any given moment. That's it. So even if you've got this beast of a machine with 8, 16, maybe even 64 cores, the GIL makes them all stand in a single file line and take turns. It basically turns your multi-core processor into a single-core one for Python code. Yeah, this is a perfect analogy. Think about it. You've got a stage full of brilliant speakers all ready to share their ideas, but there's only one microphone. Just one. So no matter how many people are on that stage, only one can talk at a time. That microphone, that's the GIL. And everyone else, they're just stuck, waiting for their turn. Now, of course, developers are a resourceful bunch. They haven't just thrown up their hands and accepted this. For years, people have come up with clever workarounds to try and squeeze some real parallel performance out of Python. But as you're about to see, each of these solutions comes with its own pretty big catch. Okay, so on one side, you've got threading. The great thing about threads is they all share the same memory, so sharing data between them is super easy. The downside, they're all still waiting for that one microphone. They're all blocked by the GIL. This works okay for things that do a lot of waiting, like IO-bound tasks. Then there's the other approach, multiprocessing. This is like giving every single process its own microphone, so it totally bypasses the GIL. Awesome, right? Well, the catch is that each process also gets its own separate block of memory, which makes sharing data between them a huge pain and adds a ton of complexity. And look, this isn't just some theoretical academic problem. This quote from an engineer at DeepMind just hits it home. The workarounds got so complicated that a team working on cutting-edge AI found it was literally easier to just scrap Python and rewrite their entire project in C++. I mean, think about that. That's how big of a deal the GIL can be. So, if the old workarounds are all kind of flawed, what's the real solution? Well, this brings us to the main event. No GIL Python. The whole idea is beautifully simple, but also incredibly powerful. What if we could just get rid of the lock entirely? And that's exactly what this does. No GIL Python just yeets that global lock out the window. It's like giving a microphone to every single speaker on that stage. And for the very first time, this means multiple threads can run actual Python code on multiple CPU cores all at the same time. We're talking true parallelism. This is a potential game changer, for sure. Okay, but this is the million-dollar question, isn't it? It's great to talk about theory, but what happens when we actually try it out? What does this mean for the tools we use every single day? Libraries like Pandas, NumPy, scikit-learn. Is everything just magically going to get faster now? To answer that, we got to look at the numbers. So let's walk through some benchmarks that put standard Python head-to-head with no GL Python on some pretty common ML tasks. This is where the hype train meets the reality check. All right, first up, let's look at the absolute ideal scenario. This is a task that's just pure Python computation. No fancy libraries, just a ton of loops and math. And wow, the results are awesome. No GL Python is about 3 times faster. This proves that when your bottleneck is pure Python code, the speedup is absolutely real and, well, it's huge. Okay, now let's bring in a library we all use, Pandas. And here, we're still seeing a really impressive 2.7x speedup, but the reason why is super interesting. See, unlike some other libraries, a lot of common Pandas operations, think about using .apply, for example, are actually running in Python under the hood. So when you remove the GIL, you directly speed up that Python code, and you get this massive win. And now for the really crucial comparison. Just look at this chart. You see that huge bar for Pandas, right? But then, look at SciPy. It's just a tiny 12% faster. And NumPy? Nothing. 0 speedup. So what is going on? Why did the magic suddenly disappear?
Well, the secret is in how these libraries are actually built. See, libraries like NumPy and scikit-learn get their incredible speed by not using Python for the heavy lifting. When you do something like multiply two giant matrices in NumPy, the library doesn't do that in Python. It hands that job off to super optimized C++ or Fortran code. And here's the kicker. That C++ code already releases the GIL. To go back to our analogy, it was already using its own microphone. So getting rid of the main microphone doesn't help it at all, because it wasn't waiting for it in the first place.
And there's one more little reality check we need to talk about: compatibility. The whole ecosystem isn't quite ready for this yet. For example, when running a benchmark on the Hugging Face Transformers library, the tokenizer just crashed. It's a good reminder that this is still bleeding edge stuff, and it's going to take a while for all the tools we rely on to catch up and become fully compatible. Okay, so we've seen some amazing speedups and some total duds. So what's the final verdict here? How should you and I think about no-GIL Python? Let's just break it all down one last time.
This table really makes it crystal clear. Look, if the work is happening in Python, like in a pure Python script or in a lot of pandas functions, the impact is huge. We're talking 3x, 2.7x, fantastic. But if your code is spending all its time running in native code, like the C++ or Fortran that powers NumPy and scikit-learn, well, the GIL was never the problem to begin with, so removing it does pretty much nothing.
So here it is, the single most important thing to remember from all of this. Ready? No GIL Python only speeds up the parts of your code that are actually running in Python. That's the rule. It's not a magic bullet. The speedup you see is going to be directly tied to how much of your program's bottleneck is pure Python code. And that really leaves us with a fascinating question for the future, doesn't it? For decades, the entire way people have written high-performance Python has been designed around the GIL. Now that the lock is gone, it's not just about making old code faster. It opens up the possibility for entirely new ways of building software, things that were just too clunky or inefficient to even try before in Python. So the real question is, what happens next? What are developers going to build now that Python is truly parallel?